Today we are going to learn the design of a linked list from scratch, which is LeetCode problem 707. We will use Java for coding. What's a linked list? It's a data structure of a storing collection of data in various forms. Unlike arrays, linked list is dynamic memory. Can be referred to as a linear data structure where traversal is possible in the forward or the backward direction, depending upon the type of linked list. It can be a singular linked list or a doubly linked list, which we will learn now. A singular linked list allows you to take forward direction. A doubly linked list allows you to take both forward and backward direction with help of pointers. Now, if we were to talk about the representation of linked list in Java, it comprises of a node that has value, which is the data, and then a pointer to the next node. This is the address that it holds for the next node. With respect to the bunch of operations, there are three sets of primary operations that can be supported on linked list. It allows insertion or addition of a node with a given value at any position, maybe to the head of the node, to the tail, or at a given index at any position. It's also possible to insert and delete across any element, maybe the head, tail, or at a given position. And then finally, we have the lookup function, which is essentially the search operation to perform fetch or get of a node at a given index. We'll take a look into the linked list by action. The pictorial diagram that you see here is a linked list comprising of 6 nodes. The head node is 21 and the tail node is 55. The head node comprises of data and then pointer to the next node. Now if we were to perform some insertion or addition to the head, as you see here, if we want to insert 33, then we go ahead, create a new node, link it up to the head of the current linked list and change the head pointer. Next, if we were to insert it to tail, we change the position of the pointers accordingly. So if 66 is expected to be appended to the tail, then we change the position of the tail from 55 to 66 by changing the pointers accordingly. Now as you see here, the next node of 55 points to 66 and the next node of 66 is terminated by null. And then if you are required to perform insertion to the middle, as you see here, it's a 50. You want to insert between 43 and 33. So that is responsible for manipulating the pointers. The LeetCode problem 707 goes something like this. The goal is to build a linked list from scratch. To design an implementation of the linked list, we could use a singular linked list or a doubly linked list. The node comprises of value val and then the pointer to the next node. We are expected to build the constructor for the main class, perform the fetch operation or get operation on a given index or a position, add data or node to the head and tail, also be able to add data to the index. We have provided with the index and value, and then also finally perform delete operation on a given index. An example is here. So we get started building linked list from scratch. Here today we are going to build a singular linked list. LeetCode of course does not limit us to what sort of linked list is to be built. It can be a singular linked list or a doubly linked list. So let's go with the singular linked list. So we know a linked list comprises of elements or nodes with data in it and an address pointing to the next node in the linked list. A simple example will be like this. Here we have 4 elements or 4 nodes, starting with the head node, that's at 1, and we call 8 as a tail node. Now we have element 1 pointing to 3, and then that points to 7, and that points to 8. So each node here will have data 1 and the address to the next link or the connector, which is 3. Given that background, we'll go ahead and build the linked list from scratch. We are here expected to build a bunch of linked list operations as to add an element to the head, add an element to the tail, add an element at a given position or index, and then be also able to remove an element from a given index. Also finally perform some search operation or lookup by way of getting. This is the constructor. We are expected to fill in the code for all of this and we get started. To begin with, our first step will be to define the linked list node. So we'll define the linked list node here. Define the node. That will be our first step. So we know our linked list node comprises of data or value and then an address pointing to a next node. So we'll declare private static class. This is going to be a list node. It's not my linked list, but it's going to be a new class where we have definition of the linked list node, integer val, and then list node. Next, this is going to be the address of the next node. We need a constructor for this so that we are able to initialize it as and when we create new nodes or allocate new nodes. So when new nodes are being called up, this is going to be step 2. We will initialize the values. So we will assume that the new node will be invoked with a value passed in. So this dot val, and then next, the next pointer of the first node that's going to be created will be null. Irrespective whether it's the first node or the nth node, we are creating a node that needs to be connected into the linked list with the value that it's passed with and its next pointer pointing to null. Further, our third step will be to define the head node. Define head and size of the linked list. Step 3 will be this. Private list node head. Private int size. So we are going to have the head pointing to list node. That's what we are defined here. And then we are also tracking the size of the list node. This can be optional in many cases, but we'll have it now. So that's our step 3. And then finally, the constructor for list node class is defined here. We have the constructor, new constructor for the linked list class getting this defined here. So constructor for my linked list. Constructors are meant for initialization. So what are we going to initialize here? we're going to initialize head pointing to null. So when we invoke it for the first time, it's going to be pointing to null, and we have no elements in the linked list. So essentially the linked list is empty, and the size also is set to 0. So with all this basic plumbing required for creation of the linked list, we build our operations. List operations are list functions. So initially our linked list is empty. We don't want to fill in this get function or lookup function when our linked list is empty. There is nothing to fetch. So we will move this implementation to the later stage. But currently focus on adding the elements to the linked list. Basically, we'll go by the way in which the linked list looks on top of our mind at any part of time. So our next step will be to add node to the head of the linked list. This is going to be step number 4. First thing here will be to create a new node with the value here. So list node new node equal to new list node of value. So this will basically call the constructor that we have defined here and here, and set the initial values for the new node that we have created. Next, we add the node to the head. Add node to head. So if we were to begin with the empty linked list, then our linked list will be null, and the head pointer that we have defined here is going to be null. So if head is null, the node that we have created right away is the first node. So add head to null. If head is empty, new node is the first node. Okay. Otherwise, we will add it to the head. So new node dot next equal to head. So we change or modify the next pointer of the new node to the head node, and then make head itself pointing to the new node. So we are done with the implementation of adding a new node to the head. Before we jump into the next operation, I would like to call upon the way in which we are going to add node to the head. Looks something like this. Initially, we have a null pointer, and if we were to call upon add to head function with a value, let's say 1 for the first time, and it's going to be something like this, adding 1 to the head. The next time we are going to call add at head with another value, say 2, is going to be prepended to the head like this. The third time it's going to be like this. And the fourth time like this, and fifth time like this. So basically whenever you're adding a node to the head, it keeps prepending. Now 5 becomes head and 1 becomes the tail. The catch is here we are not maintaining the pointer or the index to the tail, and so if we were to reach to the tail node, we will be required to traverse from the head to the tail every time we want to add a node to the tail. So when we hop into an implementation where we are required to implement adding node to the tail, will be required to traverse from the head to the current tail node to go ahead and append the new value or new node. In this implementation of adding node to the head, we are not tracking the tail pointer. So I will call this as approach 1. In one another approach, we can go ahead and keep track of the tail as well, which we will discuss in one other new session. So, as usual, we go now with implementing addition of an element or node to the tail. Add node to the tail of the linked list. This will be step number 6. Step number 5. This 4 and this 5. Okay. As usual, we will be required to create a new node. Create a new node with val. So we'll have to call list node new node equal to new list node with value. So this will initialize our node with val and then allow the next pointer direct to null. Next, we go ahead and add element to the tail. Even in this case, we need to consider or accommodate a situation where head pointer is initially null. So if we were to call add at head at a situation where head pointer turns out to be null, if head is null, then new node becomes first node of the linked list. Head equal to null, head equal to the new node itself becomes the head. Otherwise, to append the new node to the end of the linked list, we will be required to traverse until the last node, as I mentioned before, because we don't have a pointer or a tracker to the last node. In case we had a tracker to the last node, it would be easy to simply go ahead and append it. But here we don't have it, and we are required to walk over the entire linked list until we hit the last node. So while traverse dot next, so we'll be required to walk until the next node is not null. So it means that if we were to have a list like this, then traverse will traverse until this point 2. So traverse will have to stop, this loop, while loop will have to stop. When we hit 1, it will stop. So that's our tail. traverse equal to traverse dot next. So when we come out of this list, traverse will be at tail 1. And the next node to this will be our new node. So traverse dot next equal to okay, so we forgot to add an incremental when we are adding it to the head. So here and here we go an incremental size. This is actually optional, and so we missed it previously. It's fine. We have incremented. So the addition of node to the tail of the linked list comes to an end here. Next, we will add an element at a given index or a position. So if we were to require to add an element at index, let's say 4, that's here. Now 2 will have to be replaced by the new element, and 2 will have to be pushed to being the next element after the new element. So we'll have to traverse through the linked list until the position and then insert the new node. So we'll go with the implementation. So this will be step number 6. Insert a new node at a given index, or we call it as position. So this will be step number 6. So even in this case, we'll have to perform some base sanity checks to see if the given index is valid and if the linked list is not empty. If index is greater than the size of the linked list, then we can't insert it. If index is less than 0 or index is greater than size, that's beyond the boundaries of the linked list, we simply return. This is the base condition. Now if the given index turns out to be 0, then we are expecting the new element to be added to the head. So if index equal to 0, then we are required to add or prepend the new element to the head. So we simply call our implementation for adding element to the head, which we already created, and pass the value for insertion. Otherwise, we'll have to traverse through the linked list until we hit the position and then insert the new node. So as usual, we'll be required to create the new node by calling the new function for allocation of memory for the new node. So create the new list node, new node equal to new of list node with the value passed. So we need a walker or a traverser. We call that as previous and position that at the head of the linked list. We'll be required to walk until we hit index -1. I'll tell you why in a short while. Traverse until index minus 1 is hit. For int I equal to 0, I less than index minus 1, increment it, previous is equal to previous dot next. So when we are done with this loop, we will be in a position where we are at a location where the node becomes the previous node of the new node. Okay. So at this point, we are at the location where current node, that is this node, prev, becomes previous node of the new node. This node becomes previous node of this node. That needs to be inserted. So we will make new node of next point to previous of next. And previous of next point to new node. Okay, finally increment the size. We have added the node and now we are going to increment the size. Before we take a step further to implement the leftover functions, we'll see if there are any syntax errors so that we don't see them on the terminal when running the code. It looks a little messy or nasty. I see a typo here, it needs to be removed. It's okay that we fix it right away here because I see it's quite a bit lengthy code. There's a dot here. Looks okay so far. Oh, this constructor needs to be part of this class. Yeah, this constructor is part of list node, and if I put it outside here, it becomes constructor for this, which is not correct. Good. We can now proceed towards implementing our get function. Now we are good to implement the get function, which basically performs the fetch operation for a given node. So perform fetch on a given index for a given list. So we'll perform base condition check, base check. We ensure that the list is not empty. So index is greater than or equal to size, or index is less than 0, or size equal to 0. We validate across the index and the size. We simply return -1. There's nothing to fetch. Otherwise, we'll traverse over the linked list until we hit end of the list and search for this index across that. To traverse, we need a tracker. So traverse across the list. List node traverse equal to head. We make the traverse or the tracker point to the head, and while index not equal to 0, traverse equal to traverse dot next, and then we decrement the index. We return the value that we have obtained at index node. Traverse dot val will be the value of the node. So as previously discussed, if we were to have this linked list, and if index was supposed to be 3, then we would traverse until here and then fetch node 3. If it was 4, then we would traverse until here and then fetch node 2. Basically, it's 1, 2, 3, and 4th node across the linked list. For a given index, that 2 will be the value of the node at index 4. Okay, so this reminds me of not providing this somewhere here. Yeah. Okay, we have implemented the get function also. The final one that's left over is the delete at a given index. Before we proceed to implementing the last function for this design of building a single linked list, we check if there is any errors in the previous implementation. There's a typo here, and that this needs to be traverse, a typo here, traverse.val. So we'll verify this is uppercase val. So yeah, this needs to be big. And then, so yeah, so this is uppercase val. Okay. Now we implement the delete function. This has been step 7. Delete node at a given index. That is step 8, or the final step in this requirement. So we perform the base check. Again, we ensure that the list is not empty and index is greater than 0 or size. If index is less than 0 or if index is greater than or equal to size, or if size equal to 0, we can't remove. So we return and it's void here, so we simply return. Now if you are expected to remove the head node, then if index is 0, it means head node. So we just hop to the next node. So skip. So given this protocol of setting head node as 0th index, previously we had marked index 4, and if index 4 is set, then we would have 0, 1, 2, 3 and 4. So it will be value 1 that will be returned. If index equal to 4, return val equal to 1. Okay. Now this is a linked list, so we can keep the index as we like, but by following the protocol of array indexing, we can say the first value at index 0. Else, as we did with addition of node at a given index previously, we'll walk until index minus 1 and then remove the expected node at a given index. So traverse until previous index is hit. For int I equal to 0, I less than index minus 1, I plus plus, previous equal to previous dot next. So when we are done with this loop, we are at the previous node to the index of the node that needs to be removed. So we simply skip from previous to the next pointer. So skip the node to delete the index. Previous dot next equal to previous dot next, and then we decrement the size because we have removed the node entry. That's all. So it means that if we were to remove value 3 at index 2, this will be 0, 1 and 2, then our previous pointer will be pointing to 4, and at this position in the code, previous dot next will be 2 instead of 3. So we simply say previous dot next equal to previous dot next to next, so that this 3 gets automatically purged off, and we are done with implementing all the operations asked for here. As usual, let's run a quick check on our current implementation for sanity checks. Semicolon missing. There's a typo here. Let's remove that. Index less than 0, size equal to 0. Fine. Okay. Definition of previous is missing. We make it point to head. Alright. Now we are done with the implementation and sanity checks. We'll see the test case here. There's only one test case. We are good to run and get the results. Because we have performed the sanity checks in advance, we are now good to see the results in a neat fashion without any messy errors or clumsy errors. I wouldn't like to see them. Let's see. Let's try our luck. Yeah, it's always good to check or perform sanity checks on all the code written, both semantically and syntactically. Ensure that there are no errors so that we get error-free compilation. We don't want the compiler to teach us. It's better that we make the code better and clean. It's accepted. We go ahead and submit them. So we have been successfully able to build a singly linked list from scratch for the given Java implementation. This is approach 1. So as I mentioned, there are multiple approaches. The next approach would be to keep track of the tail, and then maybe you could go ahead and implement a doubly linked list. We'll see in the upcoming sessions. Nevertheless, the execution did not give us any error, but I remember now that we had to decrement the size by 1. Yeah. So go back and run again. Okay. Now we are good to submit. Thanks for watching. You've been so far hearing from Vidya. If you like the kind of videos that I'm making, consider subscribing.